Okay, so welcome back to another video. So here we have a special improper integral from 0 to infinity of, in our integrand, we have e to the negative ax minus e to the negative bx divided by x quantity square and then dx. So inside of our integrand, specifically of the inner quantity we have that this is actually in a form of a special improper integral, what's known as the Frullani integral, named after the Italian mathematician Giuliano Frullani, which states the following, that if you have a and b such that they're positive reals, and you have f of x such that it's a continuously differentiable function defined over the non-negative reals, you have that the integral from 0 to infinity of f of ax subtract f of bx divided by x dx is going to equal to f of infinity subtract f of 0 multiplied by ln of a divided by b, with the condition that f of infinity is actually, it exists / finite. That can also be the same thing applied for f of 0 as well, if that exists. So utilizing that special definition of that improper integral, we would actually be utilizing this, that definition of the Frullani integral, specifically of a specific function that we'll be, inserting into it. And using from there that we're actually going to be using some elementary, calculus techniques, utilizing specifically the integration by parts, which will help make the simplification. And at the same time, we'll find our nice generalization for the closed form, depending on what our values a and b are going to equal to. So with that out of the way, why don't we actually just jump right in? So to start off, we have our note that this specific integral over here, 0 to infinity of e to the negative ax subtract e to the negative bx divided by x dx, we're going to have that's going to equal to ln of a divided by b. And you'll notice that specifically if I just plug in our function for f of x that of our choice, we have that f of x, we're going to let this be e to the negative x. And if I were to plug in our values, so f of infinity, well, if we take that limit as it approaches infinity, rather, we get that that's just going to equal 0. And then if I have f of 0, then that means that's just going to equal just 1. And then that would have to mean that if I just plug everything back together, so that means 0 to infinity of e to the negative ax subtract e to the negative b times x divided by x dx. Then utilizing that definition of what the Frullani integral states, we have that this is f of infinity, which we said that is 0. I rather should say f approaches infinity to that extent. Then subtract f of 0, which is 1, and then multiply by ln of a divided by b, which simply is just equal to the latter above, ln of a divided by b. Okay, so with this in mind, we'll actually be now utilizing this step to eventually later in the middle of processing of after applying the integration by parts that we will actually be utilizing this definition. So let's actually now get into the real meat of our evaluation. So our integral we're going to work with, so let me call this capital I. So that means capital I, then suppose that if I choose our u substitution, we're actually, well, not u substitution, our integration by parts, we want to choose our u that we want to calculate the derivative of, and our dv that we want to integrate. So we say that du, or not du, we're going to let that function be the numerator if we distribute the square to both numerator and denominator. So u is going to equal to e to the negative ax subtract e to the negative b times x, then quantity square. So that means differentiated, I have that I apply the chain rule, so that means it's going to be 2 multiplied by e to the negative ax subtract e to the negative bx. And then that exponent will become a 1. And then we take the derivative of our inside of our quantity over here, our exponential function. So what we have is, and because it's a negative over here, when you apply that derivative, I'm actually going to move that to the front. So I have b, then e, negative bx, and then subtract a, then e, negative ax, and then this is going to follow with dx. Okay, and so with this, now we choose our dv. We're going to let that be 1 divided by x squared, and then dx. So our v then is going to be negative 1 divided by x. So in standard integration by parts, we have that the formula, we actually multiply our u and v, then subtract with the integral of v times du. So with that, let's actually put that back together over here. So what we have now is going to be, so negative, then this is going to be e, then negative ax minus e to the negative b times x. Let me actually write the constant first in front of the variable. So bx, then quantity square, and then divided by x, then we have to evaluate this from our bounds to 0 to infinity. And then now let's actually subtract, and we have a negative multiplied to the du from our v, so I can actually factor out not only the negative, but also the 2 as well. So that's going to be a plus 2. Then our integral from 0 to infinity, and then now just put everything back together. I have b e negative bx subtract a times e negative ax multiply by e negative ax and then subtract e negative bx, then all this being divided by x and then just followed up with dx. Okay, and so the last thing is that we need to be careful here as we have an infinity and 0. We notice something of an indeterminate form, so we got to be careful how we do this. So let's actually calculate our limits here one at a time. So I have the limit as x approaches infinity. First we have negative, then e negative ax, subtract e negative bx, and then divided by x. Well, simply I have that infinity is going to approach here. That's going to be infinity over here. But if we put this at the top, that means I have a 0 and a 0. So I have a 0 over infinity. Not exactly indeterminate form, but it actually does mean that this is actually just going to equal 0. So no L'Hopital needs to be applied here. Okay, however, now if I have the limit as x approaches 0 of the same thing, so negative and then e negative ax minus e negative bx, then divided by x, that's supposed to be a square here, so square, but thankfully that doesn't change much. So square, and what we see here is, of course, this is going to be a 0 over 0 indeterminate form. Then if you were to apply L'Hopital's rule, so that means I can take the derivative of the numerator and the denominator respectively. So this, the denominator is just going to be 1, so thankfully that just gets that out of the way. So I have that this is x approaches 0, so that means I'm just taking the derivative of what we just did from up here. So now this is going to be 2, then or rather negative, and then negative 2, so e negative ax subtract e negative bx. Let me fix that first. And then multiply by b e negative bx, then subtract a e negative ax. Now, if I just plug 0, so that means that's just going to be a 1, 1, but that means that's just 0 over here. So that means that whole thing's just going to approach 0. And so therefore, this value over here is simply just going to be 0. So that at least that narrows everything down and reduces things a little bit easier. So now all we're left with is we have to evaluate our integral over here. So actually, let me go back to the purple here and then we can actually continue from the blank space. All right, so our integral left we're dealing with is this following over here. So what we can do here is let's actually now perform our multiplication for the FOIL method. So what I have now is that, and you can also jump one step ahead and simplify everything out, that we're gonna have the following. So this is gonna be 0 to infinity. What we have now, we're gonna have b, then e to the negative x multiply, so the quantity is b plus a. Then next I have negative b, then e, then negative bx. Or actually, it's actually twice that quantity, so 2bx, negative 2bx. And then next afterwards, after continuing forward, I have that this is going to be a, and then multiply by e to the power negative 2ax, and then add this with a times e, and then to the power negative x multiplied by b plus a, and then all this being divided by x, and then dx. Okay, so we can actually split some things together, applying the linearity, of course. So what we have is, and because I'll also factor out the constants b and a after, applying that same linearity, what we have is we're gonna have 2b, then multiply integral from 0 to infinity of e to the negative x times b plus a, and then subtract e to the negative x, and I could write that as 2 times b, all this being divided by x and then dx. Then you just do the same thing for the a quantity, so plus 2a multiplied by the integral from 0 to infinity of e negative x, then b plus a, and then subtract e to the negative x, then times 2a divided by x, and then dx. Okay, and this is why I justify by saying that we can actually now utilize this definition of that basic Frullani integral in terms of the function f of x equals e to the negative x. So with this in mind, we can actually just put in that standard substitution utilizing that definition, and we get something of a nice, interesting closed form. So what we have now is that this is going to be in reduced to, so 2b multiplied by ln, and I'm just going to denote the absolute value for the positive. So, well, it'll be okay because since everything for A and B is all positive, but I'll just leave this out here anyway, just cause. So 2b and then divided by, so b plus a or a plus b. I'll write a plus b first instead. And then add this with 2a, then times ln of now 2a divided by a plus b, close that off. And then we can actually simplify it further. So I have ln, so now I'll just put in the parentheses now. So inside I have 2b and then divided by a plus b, all this in the quantity of to the power 2b, then multiplied by, now it's just the same thing except it's just a, so 2a, a plus b, and then to the power 2a, and then we can simply reduce this down to applying the natural law properties. I have ln of, now we have, so 2b to the power 2b, then 2a to the power 2a, and then all this being divided by a plus b, then to the power 2 times a plus b. And so with that, that's actually our final answer of our nice generalization of the Frullani integral type. And so it actually just leads down to a nice natural log function of that pinnacle. So that's nice. Both A and B are both positive reals, and I could write the absolute value if I wanted to, but they're positive reals, so at least it's always going to be positive regardless. So leaves down to that, and then we actually just utilized our basic Frullani integral type that we actually utilized the simple definition of that type that put in that substitution afterwards for b plus a, and then 2b and then 2a, which leads to this. So there you have it. Yeah, that's pretty cool if you ask me.